welcome to the deep dive. Today we're tackling a really core systems design challenge. We're trying to solve this massive technical puzzle, scaling large language models. Our mission is to really get under the hood and understand why context length, that's how much text an LM can remember once, why it's become such a huge divider in the field.
It really is a fascinating gap, isn't it? You look at these popular open source models, and they seem to hit this wall, maybe around 32,000 tokens. But then you see the big industry players, and they're talking about 128K, sometimes even 1,000,000 tokens. And it's tempting to think it's just about having more GPUs, more money, but it really boils down to something more fundamental, an architectural barrier.
Okay, right. Let's dig into that, because when you think about why a model might sort of break down when the input text gets really long, well, you might naturally assume it's just running out of memory, raw RAM. But the sources we look at are pretty clear. The real bottleneck is much deeper. It comes from a specific part inside the transformer itself. What is that core pain point?
Yeah, the pain really stems from the self-attention mechanism. Fundamentally, what self-attention means is that every single token in your input sequence, it has to calculate a relationship and attention score with every other token. So if your sequence has length n, the amount of computation needed, it scales quadratically. Engineers call that ON1. That's the wall. That's the barrier.
Let's maybe put some numbers on that quadratic pain using the examples from our sources just to make it concrete.
Sure. So take a fairly standard context size, say 8,000 tokens. For that, you're already looking at roughly 64 million attention computations. Okay. Now, let's imagine scaling that up to 1,000,000 tokens. You might think, okay, that's about 125 times longer. But because of the quadratic scaling, the compute doesn't just multiply by 125. No, it explodes. You end up needing a staggering 1 trillion attention computations. The cost just goes through the roof. It makes really long context windows mathematically almost impossible with that standard architecture.
Wow, 1 trillion. And you're saying this cost isn't just the compute time, it's also about memory, right? It's not merely storing the input text itself, it's storing all those potential connections between every single word pair.
Precisely. Exactly. The system literally has to build this massive grid in memory and n-by-n attention matrix just to hold the scores for every possible token-to-token relationship. For that 1,000,000 token example, you're trying to find space for and calculate 1 trillion floating point values just to map out that web of connections. That constraint, that massive matrix, is basically why most developers using standard methods get stuck around that 32K limit. It just becomes computationally and physically too enormous.
Okay, so this is where it gets really interesting then. How are the industry leaders, the ones hitting 128K or even that 1,000,000 token mark, how are they getting past this ON wall? They must be, cheating the quadratic math somehow.
They are. Well, maybe cheating isn't the right word, but they're using a clever architectural fix. The main one is called sliding window attention, or SWA. The core idea is instead of making every token look at the entire sequence, you only make it attend to a smaller, fixed, local window of tokens around it. Let's say that window size is W. And that simple change, it immediately breaks the quadratic scaling. The complexity drops way down to something much more manageable, ONW.
Okay, ONW. So linear in sequence length n times this window size w. That makes sense computationally. But wait, if a token, say token number 1, can only see the tokens right next to it, maybe tokens 2 through 50, how does the model build up a global understanding of a really long document? How does it connect something at the beginning with something right at the end if it only has these local glimpses?
That's the elegant part. It's a conceptual trick that's actually borrowed from computer vision. Think about convolutional neural networks, CNNs, used for images. A CNN starts by looking at tiny patches of pixels, right? Very local views. But as the information flows through many, many layers, dozens of them, those local features get combined and combined again, and eventually the network builds up a complete global understanding of the whole image. SWA works in a similar way. You have local attention happening in each layer, but because these models are deep, often 30, 40, or even more transformer blocks, that local information gradually propagates across the entire sequence. So information from the start can eventually influence the end, even with just local windows in each step.
That makes it seem much more feasible. It's like layers building on layers. Our sources also mentioned a specific kind of practical implementation detail, a trade-off they make to get this running efficiently.
Yes, that's important for actually building these systems. To make SWA run fast on current hardware, like GPUs, you typically have to split the query and key matrices. Those are inputs to the attention into overlapping chunks. Then you perform the attention calculation within those chunks. Now, this method, because of the overlapping, might actually compute slightly more than the absolute theoretical minimum for SWA, maybe about twice as much. But here's the key trade-off. That small bit of extra work is what takes you from a system that's basically impossible due to the ON math to a design that can actually run realistically on maybe even a single high-end GPU. It's a pragmatic choice. That's often what great systems design is about, finding those practical compromises.
Right, that trade-off makes sense. So let's summarize this for everyone listening. What does this deep dive really tell us? Scaling context length, getting those million token windows, it isn't fundamentally solved by just throwing more hardware, bigger GPUs at the problem. It's all by being clever, by breaking that tough quadratic math using architectural innovations like sliding window attention.
Exactly. The underlying mathematics dictates the limits you face, but clever architecture provides the workaround. It's an architectural solution to a mathematical bottleneck.
Okay, so we spent this whole deep dive figuring out how models can achieve these huge 1 million token context windows. But the final thought, maybe the more provocative question raised by our sources, and perhaps the one that really tests the system designer, is this. Now that we can potentially break that ceiling, do we actually need 1 million tokens for most typical real-world applications? That tension between pushing the capability versus understanding the practical necessity, that's definitely something worth thinking about. We'll leave you with that thought. Catch you on the next deep dive.